Hi, welcome to Modern Optimization Methods. Today we will introduce the last part of Chapter 7, the duality theorem. Now, note that duality is actually an important part in optimization algorithms, especially for the later introduced augmented Lagrange method. And also, duality theorem provided another point of view to do linear optimization, and also it actually states important insight to the fields of convex optimization problems. So to address the duality theorem, let's first take a look at the KKT conditions. Now, recall that we are considering a constraint optimization. So at this moment, we consider only the inequality constraints. Okay, actually for the equality constraint case, it is similar. And here we write down the constraint C in terms of a vector constraints. Okay, that means for each component here we got Cix must to be positive or equal to 0. So this is for the constraint. And from this point of view, then we can give the Lagrange function, which is, we write it in the term of vector form. Okay, so here we use lambda transpose Cx to represent the sum of each lambda I multiplied by Cix. Now, after introducing the Lagrange function, then we can have the following results. So we define firstly the new function q about lambda by choosing the infimum of Lagrange function with respect to x. Okay, so recall that the Lagrange function is actually two parts of variables. So x is the first part of variables, and lambda is also sort of variables. So we take the infimum about this Lagrange function with respect to x in the four-dimensional case. Then we get another function called q lambda about lambda. So this lambda is actually important, and it will be the dual objective function. Notice that in many cases, the value of q lambda will be negative infinity. Okay? Due to this observation, we can define the effective domain as the following. So we define the domain of q as those function values which achieves greater than negative infinity. Okay, all the x or all the variables which have finite function values will be collected in this region D. The dual problem is then defined as the max of q lambda, such that this lambda should be non-negative. So the non-negativity actually comes from the fact that we have Cx here is inequality constraints. Okay? So this is the dual problem. Let's take a look at an example how we can get the dual problem. We have this minimization of a quadratic function subject to a linear inequality constraints here. So according to our way to generate the dual problem, we first write down the Lagrange function, which is the objective function minus lambda I multiplied by the inequality constraints. After that, we take infimum of the Lagrange function with respect to x, which means that we try to find the minimizer of this Lagrange function with respect to x1 and x2. So to do this, we divided them for several steps. So at the moment here, this lambda is actually a fixed parameter, which we assume that it is given. Then after that, for this Lagrange function, as we can see that in terms of x1 and x2, it is actually a strongly convex function, okay, with respect to x1 and x2. Therefore, to get the minimum solution, then we can just take the gradient of this function with respect to x to be 0, then we can find the optimal solution x1 and x2. Therefore, by taking gradient to be 0, then we can find that x1 is actually lambda 1 and x2 is 0. In other words, if we substituting the minimization point into the function values, then we can find the minimum value of this Lagrange function, which is our q lambda I. Okay? Therefore, for the dual objective function q, it is actually only related to the variable lambda 1, and the formula we already calculate it like this. Okay, so this is the dual objective function. After that, the final step is that we take the maximum of the dual function. Okay, so the dual function is here. Meanwhile, we require this lambda 1 to be non-negative. Therefore, this is the dual problem. And we can easily see that the optimal solution for the dual problem is actually achieved at lambda 1 equals 1. So this example actually demonstrates that how we can derive dual problem for example. Now, to summarize the dual problem, the objective of the dual problem take the following form. Okay, we have to take the infimum of the Lagrange functions with respect to x. So given a particular problem, it may not that easy to find the dual objective, okay? Because you may got complicated functions or complicated constraints, which may prevent you to find easy solutions for the infimum here, okay? On the other hand, when this f and minus ci, they are all convex functions. In other words, when the problem is a convex problem, then we can easily find that the dual function is also convex. All right? So in this situation, all the local minimizers, they are global minimizers. Therefore, the problem will be easier to get. Okay? So as we mentioned in the previous example. So this is a very special case. So now let's talk about the duality theorem. We have two theorems about the duality. So the first one is that the function q is always concave and its domain D is convex. So this is a very interesting result. So no matter the primal problem, whether it is convex or not, we have the dual problem is always q is concave and its domain D is convex. In other words, the dual problem, if we transfer it into a minimization problem, it is a convex problem. Okay? And the second result is that there is some relationship between the primal problem and the dual problem. The relationship basically says that if we take any feasible point for the primal problem and we calculate the objective function, and for any dual variable lambda bar, which is satisfying the constraints non-negativity, then we have that the dual objective function is always smaller than or equal to the primal objective functions. In other words, the dual problem will always have function values not exceeding the primal one. Okay? So this is called the weak duality theorem. Of course, we have some strong duality theorem under some very special constraint qualifications. And now, let's take a look at the KKT condition. So recall that for the KKT conditions, we have now rewrite them in terms of vector form. Okay? So the vector form actually means that we rewrite the gradient of constraints in terms of column vectors here. And then the first part of KKT conditions can be rewritten as the gradient of function minus the gradient of constraints multiplied by the Lagrange multiplier lambda bar. The other parts of the KKT conditions are the same as before. And after this formulation, then we can see that the following strong duality theorem. So let's take a detailed look at what this theorem says. So we suppose that x bar is a solution of the primal problem, and f and minus ci are convex functions. So this basically means that we are considering a convex optimization problem. Assume further that the function and the constraints, they are all differentiable at this optimal solution x bar. Then for any lambda bar which satisfy the KKT conditions, we can have the result that this lambda bar is also a solution of the dual problem. In other words, at an optimal solution x star of the primal problem, the solution for KKT conditions also corresponds to the solution of the dual problem. Okay? So in other words, if we can successfully solve the KKT conditions in the convex case, then we can get the optimal primal problem solutions on one hand, and meanwhile, we can get the optimal solutions for the dual problem, which is very nice. Now, let's take a look at another example, which is about linear programming. Okay? So for linear programming, we got linear objective functions and also linear constraints. Here, we also consider the inequality linear constraints. Now, following the way of writing down the dual objective functions, we can see that the Lagrange function is like this, that we minimize that the primal objective function here and then minus the Lagrange multiplier multiplied by the inequality constraints. So this is the Lagrange function, and we minimize this Lagrange function over x to get the dual objective. So how can we derive this infimum? Because we are trying to minimize it with respect to x, so we reformulate this function in terms of x. Okay, so we write it as a linear function about x. Therefore, the linear term of x will be this part, and the constant term will be b transpose lambda. So for a linear function, we got a coefficient like this. Okay, so if we try to take infimum in the whole space, so think about this, how we can get the infimum. Of course, notice that the coefficient here is actually not specified. Okay, it is related to lambda. So we have to discuss two different cases. The first one is that if this coefficient here is not 0, in this case, it means that we have a hyperplane over the whole space, all right? Therefore, by taking x to be this part, to be the negative of the coefficient, we can always take the infimum to be minus infinity or negative infinity, okay? So in this case, for case 1, the q lambda will tend to negative infinity. For the second case, if we got this coefficient to be 0, in other words, it is a constant function with respect to x, then, of course, the infinity is this constant itself, okay? Therefore, if we summarizing the two cases, then we can see that for q lambda, this negative infinity part, we can exclude this, okay? And if we take the maximum of this q lambda, then of course we will take this part, okay? And for this part, in order to get this part, we have an extra constraint here that we need to make sure that the coefficient to be 0. So in a word, we try to maximize q, therefore the dual objective function will be the b transpose lambda, which is a constant with respect to x. Meanwhile, we need to make sure that lambda is non-negative, and also we have to make sure that the coefficient about x is 0, which is this equality constraints, okay? So by deriving in this way, we can actually get that the dual objective function and dual problem for linear programming. Now, let's make a brief summary about this part. In this part, we have introduced the dual problem, including the dual objective as well as the corresponding constraints. We also demonstrate by two examples to show you how we derive the dual problem in practice. Okay, let's make a brief summary about this chapter. Actually, in this chapter, we basically introduce how we can check the optimality condition for constraint optimization problem, including the first order necessary condition, the second order necessary condition, as well as the second order sufficient condition. Finally, we also discussed the duality theorems, which is an important part in constraint optimization. Okay, so we stop here and see you next time.